Okay, let's go to the familiar, I hope familiar equation of a RLC circuit, for an RLC circuit. E of T is your applied voltage, and here's your voltage drops across the inductor. Remember, the inductor loses voltage proportional to the rate of change of the current, because inductance, if you change the current, you get a magnetic field that creates an electrical or a voltage that opposes the change in I, Lenz's law, and hopefully you're familiar with that. Resistance times your current, which is very standard and obvious definition of resistance. And then your reciprocal of your capacitance times the charge on your capacitor, and the charge on your capacitor is the integral from whatever time we started to T of the current. Okay, so there it is. There's the equation. It's very easy to transform it. We've let I of 0 equals 0 to make it easier. It could be anything, but if it's 0, then the Laplace transform of di dt is just S times L of I. It would be negative I of 0 plus L plus S L of I, but I of 0 is 0, so we don't have to write it down. And then it's R times L of I. And I've got to keep my L straight, because the fancy script L we use for the Laplace transform is different than the inductance L. They have nothing to do with one another. Okay, so there. And then it's 1 over C times the Laplace transform of I of T over S, and it's the I of T that's divided by the Laplace transform of I of T divided by S, because of course that's the transform of the integral. Okay, so there we have it. The Laplace transform of your I then can be isolated. We can factor that out of here and here, and we get SL plus 1 over CS, and that equals then the Laplace transform of whatever your voltage function is, minus R times Laplace transform of, we have another one, and that was really kind of ignorant. Let me rewrite it. Okay, so again, factoring out our L of I, every term over here has an L of I. And this thing in here we call our transfer function. So L of I is L of E of T, the Laplace transform of E of T, over this. Now there's algebra to be done, and the way we do the algebra, well, we're certainly going to multiply numerator and denominator by S and probably by CS, and then it's kind of going to depend on what our E of T function is, but there it's going to be, and it's pretty straightforward. Using the fact, of course, that the Laplace transform of the integral of I of t dt is the Laplace transform of I of t divided by s. Then your I is going to be L inverse of all this stuff. This could also be written as I don't want to write it. Just remember, this is a function of s, this is a function of s, and there we have it. I thought I saw a good notation for that, and I changed my mind. If e of t is a sine or cosine function, or an exponential function, or some easy function to integrate, of course, then you just have a non-homogeneous second order, well, it's not a second order equation. Yeah, we'll leave it as it is. This could be written as a second order equation in Q, the charge on the capacitor, and you'd have second derivative of Q, first derivative of Q, and Q here. And then you just have a non-homogeneous equation. And if this is something you could easily integrate or use for trial function, or use in a variation of parameters, then you could do that. However, a lot of times, if you have that sawtooth that we looked at earlier, then the Laplace transform of this function is not going to be as nice. And you're going to be pretty much in Laplace transform space in order to solve this. Okay, there's an example in your book. It's a good example. It has all the numbers here for the L and the R and the C, and it has a function for e of t, which is a multiple of a transformed Heaviside function, translated Heaviside function. And that can be kind of typical. You apply a constant voltage, you just hit that voltage at t equals 0, maintain it for a little while, and then just let it drop off and then see what the circuit does. And graph it. And it's pretty neat. I'll also mention that this has a complete analog with like a spring mass dashpot system, where you have a force, so this would be a force applied to the system. You would have your restoring force constant. For example, if you have a spring, you would have a drag force proportional to your velocity, which is the derivative of your position, and so forth. And you'd have a complete analogy, and you'd have essentially the same equation in terms of your velocity here. The whole thing would be solved in a completely, not even almost analogous, but in a step-by-step, once it's set up, identical fashion. So, and that is, for example, you've got a pendulum in water where you have some drag force when it moves, and you give it a brief push. From the time you start the push, that accelerates the pendulum and results in a motion that's not simple harmonic until you release it. Well, and then it's not simple harmonic because you have the drag force and so forth. Okay, well there we have it.